All right, so here's the inaugural. Oh, so we're gonna hide you. We can hide you. Okay, there we go. The inaugural week 1 dynamics. But Dr. Dale, we already mentioned this. You know this, of course. This will normally be Nathan Green is going to be running this, and I might come up next week. I might show up just to make sure he gets situated and that kind of thing. The week before each exam, I'll be doing a 2-hour session here, same room, and there'll be exam review session. This mostly, hopefully, will be interactive, where you will, I don't want to have an additional class. You're already taking the classes. This is supposed to be, the recitation is supposed to be, examples, but also I want you to be more interactive. It's a little bit more loose. So there's sort of like where we are in the schedule. I have a Blackboard page for this, so I really encourage you to register for that. Of course, this is a 0 credit class, so it doesn't really matter if you register or not. It's just if you do register, you'll get access to the Blackboard stuff. And we'll try to put up notes and things, and it's not like we're denying people the information, but it's a nice thing to have as an organization. It just, by having this be a class, by having this to be a class, we can pay the student to do this, right? So that's one of the reasons why we have this as a class. So it'd be good to have people that are registered for it, just for the provost office and that kind of thing, and to demonstrate that we as a department or as a college are trying to help out students in a class that has, it's not a terrible class, but it does have a bit of a reputation of being really difficult. People sometimes struggle with it. One of the reasons why it's a really important class. It's an important learning moment. So I really encourage you to register for the class. There's also a mechanics and materials one that's earlier in the day. They unfortunately have the same course code of ES191. So if we want to register for both, there is a form an add drop form I already pre-filled out some of it for you that you can put in and just get your advisor to sign it and send it to the assistant dean or associate dean, and you'll be registered for both classes. But doing it electronically has been problematic for some people because they already have an ES191. If you sign up for one of them, it gets mad at you for trying to sign up for the other ES191. I've tried to change this, and apparently it's immovable. I don't understand why. But anyway, there'll be other content up on there, and so I have examples from another book that I provided the solutions to the student. I advised him that he works through those examples himself before the class, and then we're going to give the problem statements are up on the Blackboard for this ahead of time, and then a PDF of the slides as well for anything up here. So let's get into it. So I use an equation sheet. I believe the other two professors, Dr. Orlip and Dr. Arica, we work closely together. I'm the course coordinator. I was the unofficial. I guess I was originally told I'm the official one, so yeah, congratulations to me. And we do meetings and try to decide, hey, how do we want to approach this? And we're always trying to improve the class. So I use an equation sheet in my class instead of having the students make an equation sheet or make an open book or whatever. It's just, I find that it just, and I can justify it, but that's what we do. All right, so I can give you more of an explanation if you felt that that's an unfair thing. We'll have a discussion about it. But for today's session, we're only covering one class. Obviously, we just had one, and the big equations are pretty just kind of simple right here. I mean, stuff that you kind of already knew, and I want to put them up on the big board here. I don't think the camera's going to catch me do that, but we know that the velocity is the time rate change of position, and acceleration is, of course, the time rate change of velocity, and therefore, I always get this 2 in the wrong spot. There you go. So, there you go. I did it right this time, or not. I don't know. That looks right. But it also has a weird one where it's the velocity times the time, not the time rate, but the position change of velocity. So this is always a strange one to put in there, but we'll see that there are some instances where that's useful to us. I tried to pitch the approach to the course with a long list of things, but amongst the important things I think will benefit you is before class, you could just peruse the book a little bit. Just look through it. You don't have to read it. Spend a minute, 5 minutes. I think you'll get a benefit for whatever amount of time that you put in, but just a little bit, just to get an idea of what the topics are. On my Blackboard page, at least, I have learning objectives. You might want to read through those. There's a couple videos. You might want to you don't have to spend a ton of time, but having that little familiarity before the class can really reap some rewards because it helps them have your mind engaged during the class. Everybody turns their brain off when they hear people talk for too long, right? I have attention span of probably a small animal. And just, I have to find ways to reset. I used to draw cartoons during lectures and try to make them relevant to what was ever being said, right? To kind of just stay engaged, have something that somehow keeps my mind working and questions that I might ask. You can think while you're looking through the book. Going through, trying to be as interactive as you can during class, but then just before you start to approach a homework problem, consider reading this section. In every section of the book, they have this part called solving problems on your own. And it kind of gives you, there's a lot of words there, I got you, but it kind of gives you little guidelines of the things that you want to do, the thought processes that you want to give, you're going to say, okay, if you need to find velocity and position when you're given acceleration as a function of time, here's the approach that you might want to use. If you're, say, given, if you want to find velocity and position, and you're given acceleration as a function of position, here's the approach, and so forth, and the other alternative, right? So it kind of gives you sort of a little bit of a guideline, and then even a little chart right here that kind of breaks down. And of course, they were describing that in all that text. So I just want to give you sort of a heads up that that's there. It's very valuable.
Oh, did you say the book was in the bookstore?
I believe the book's in the bookstore. And if you look really carefully, I think you can find it online. Don't tell me. But not this edition. But the edition you use doesn't really matter too much, right? Because we're providing problems, right? We're providing the problems for you, so you don't have to have so a lot of times if you say, it's a problem, 1135, you need this edition because they change the problem numbers every year. Sometimes they actually even change the problems. Sometimes. But yeah, it should be in the bookstore. Truthfully, your statics teacher should have told you to buy the double book. So you can go back to them. All right, so this is for you. This is not more lecture as before you guys came in. Oh, by the way, there's a sign-in sheet, so please. And all the instructors, in some way or another, are going to give you bonus points for having attended. So make sure that you sign in for just to get credit for having attended. Because I think this, it's great that you showed up. I appreciate it. So I have a number of problems right here. You probably haven't seen these, because you're not registered for the class, but these problems will be up on Blackboard, so you'll see ahead of time, and usually they go, hey, you pick which one we want to start. But let's start with this one. What do you say? So the most important first step is, I think, okay, so I can tell you my approach. When I approach a problem, right, obviously I start to read the thing, but I like to make a little diagram myself, right? And not rewrite the whole thing, the problem out, but to write out what's the important stuff. What's the important things going on here? So, all right, the car on the left, but now he's underneath it because I moved him. In the photo, I guess it is on there, moves in a straight line such that the short time its velocity is defined by, for a short time, this right here. And remember what kinematics is as we're doing this right here. One important aspect when trying to solve a problem is problem identification. What kind of problem this is? Well, first off, because that's the topic du jour, it's kinematics, right? And it's particle kinematics, but later on, if you were to do a problem, you'd want to first go organize your brain and go, what kind of problem? Oh, it's particle kinematics. Okay, then you see, oh, moves in a straight line. Like all these word problems, you want to try to, we're looking for clues as we're reading the thing through. We're jumping at what's the main given equation right here. So we have, it behaves this way. We take a look at this equation, we start to think about what that is. We say that's a square by time, so maybe in our heads we even let's say, okay, time, this is velocity as a function of time. We think of it in those terms. And I don't know what this looks like, but it probably has something like this right there, right? Some kind of parabola, some type of curve. It's got it with a bend to it, right? It's not a crazy bend like the cubic, but it's just a regular old kind of smooth bend kind of thing. All right. We want to determine the acceleration. So we want to find the acceleration. Well, I want to write A. Acceleration at t is equal to 3 seconds. Something other also, and a lot of times it might even be right there. Write the given down in there. The given and the find amongst the givens, which we also know, at t equals 0, s equals 0. Okay, so s, they're saying s, they mean that that's the position, right? They could just as easily have said x. It's a little weird in here because they haven't really quite told you that they were going to use s. It just sort of jumps out at you, right? Yeah, that's kind of weird. But one of the reasons why, by the way, is that, like, not times it doesn't, at this point, we're just treating it like one dimension, but one dimension doesn't have to be a straight line for us. It could be like this right here, right? We don't care just yet. We're going to make 2 dimensions pretty soon, but right now we're just thinking of it as something. So they're just saying that this dimension s is somewhere along the curve, right? But they did say it was a straight line, so it isn't that way, right? So the first thing, now the next thing that we want to do is then go, okay, and this is probably where most students in a problem, not necessarily this problem, but in a problem, they get stuck, right? They write down the stuff they know, and they almost get this paralysis. Like, man, for a whole lot of reasons. I think some of it's just like fear of failure. Sometimes it's lack of confidence. Anybody read Watership Down? No, it's a book about rabbits. It's fun. But the rabbits experience this. I'm going to get the name of it. I think it's not called Karn. They have a name for it, but it's that like paralysis because of fear, right? That you just kind of like, and you just need a little nudge. Well, I'll tell you, one of the secrets to being a problem solver is faking confidence, right? It's got to fake some confidence, take a chance, write something down. Maybe it's going to be wrong. One of the bad parts of requiring engineering papers that students don't want to, have to erase their engineering paper. But one thing you could do is just take some scrap paper and try the problem out, the first parts of it anyway, just to kind of try some shit out before you maybe make a commitment to one thing. Then you don't have to worry about that fear of messing up your pretty green piece of paper, right? And solving problems, a lot of dynamics problems, a lot of times, is just like going down a maze, right? You start down and you might go into a dead end. That's all problem solving, really. I mean, sometimes you might, because the problem's easy enough, or you have enough experience, you can kind of say, oh no, I should have gone this way, right? You don't always know. So sometimes you have to just take a chance, go down a blind alley, find out, oops, got stuck. But the process of doing that, even if you're wrong, will help you. All right, so the thing that we want to do for this particular problem, problem identification, we know that it's particle kinematics. We know that now it's not a constant acceleration problem. It's not a constant velocity problem. Velocity is a function of time. Therefore, we have to use fundamental kinematics. That's our idea. And then we go, we start to see, well, okay, we want to find the position. Oh, we want to find the position too. So we also want to have the position at t equals 3 seconds. So I didn't write that down. They want the position and the acceleration. I should have known that first. So because they asked for position first, let's try to figure out how do I find the position with this? And I ask you that. What do I do?
You know that the velocity is the derivative of the position function, so you can integrate the equation you're given to find the...
Exactly. And so we use this guy out here, right? So we rewrite him out. We rewrite the velocity is equal to, and now it's going to be ds dt because they decided, they're crazy maniacs, decided to use ts onto the thing. And we say that we're going to have velocity dt is equal to ds. And we're going to integrate that. So we replace this velocity with this equation. It's a function of time, so we can integrate it with respect to time. I'm going to turn the thing off so I can get rid of the light. This is bothering me. There you go. And this thing is not making me any happier either, but that's all right. We'll be all right. So 3t squared plus 2t dt equals integral of ds, and then we put the limits into the thing. And even though sometimes we might be given some numbers, but it's really nice to create, I'm not sure if any of our homework does this, but you'll notice sometimes in some problems, it's just a better idea to stick with variables for a little while and then put the numbers in. In this case, I think that should have been s is equal to 0. I didn't finish that. Right here, I'm going to put the introduction one, which is going to be 0. Happened. This is the 0 time. Happens at the same time as 0 position. So some people might think, hey, let's go ahead and put 3 right in here, right? Because we want to find when the time is. It's not wrong in this case. I'm just saying in some other problems, it's better to write out an equation and then put the number in. But so let's keep it as a variable right there, even though we know it's going to be at 3 that we're going to want to know. And here, this is a variable because we don't know this right here. So what we end up writing for this is going to be 1/3 t cubed, right? So that's just going to be t cubed plus 1/2 t squared. So that's going to be t squared, right? Because it was times 2. And this went from 0 to t. I guess I'll put this in there, but it's not really necessary in this case, right? Is going to be equal to, this is just s, and of course this is going from 0 to s. And of course what I just did right there is a completely unnecessary step, but we might want to do it in some other cases right there. So we're just going to say t cubed plus t squared is equal to s. Or write it the other way around, and then say, I'm not sure if I'm outside of the focus of that thing. At t equals 3 seconds, we're going to find that s, when we plug it in, is 36 feet. And just for the sake of emphasis, completely unnecessary in this case, because it's a whole number, give me an extra sig fig. And then I think you already kind of alluded to how we do the second part of it, right? We wanted to, also very important, make sure you go back and read the problem again. They were asking for acceleration as well, right? It's easy to miss that. So it's a really important thing when working on a problem that you have to go back and read what the original thing was asking for. So we need acceleration. How do we approach that one? Yeah, that's good. Another way of saying that. We take the derivative of it, right? Other way around. I think that's what I think we understood what you meant.
Yeah.
Take the derivative of it. So we just take acceleration is going to be equal to dv dt. And we're in luck. We don't have to do any tricks to this right here. So we can just take 3t squared plus 2t, take the derivative of it. We have what? 6t plus 2. So acceleration as a function of time right there. So we just go at t equals 3 seconds. See, make sure I did that right. Sure. You can just go ahead and write the thing out. I don't care if you could stick the numbers in. Maybe you should ask them to stick the numbers. I don't know. 20. Well, this is a pretty easy question. You know, it's good to start off with something easy, I think. Not too bad. See how we did with the. Oh, camera didn't capture some of that. Darn. I'm not sure I'm going to publish this or not. Maybe. We'll see. All right, so what do you want to do next? So this is your time, right? We have one that's this is a constant acceleration problem. So I would rather we're going to do some constant acceleration problems in the next class. So I'd kind of rather go on to one that's a little bit more complex. Let me erase some of this. I find the ones where acceleration is a function of velocity are kind of harder than some, especially the integration. It just seems that it's tough to maybe create a problem that isn't doesn't require like you to get your higher complex integration tables out. But I allow people to use on the homework at least Wolfram Alpha if you just want to kind of drive yourself crazy, because I was never good at algebra. And it's actually the part that I usually find I struggle with when it came to calculus and trigonometry is my algebra skills just weren't very. Okay, here we go. The acceleration that is a function of velocity. It even tells you at the top as part of the active thing. But once again, that's a lot of times that's part of the, the first step of the problem. Like, what is this a function of? And then you could go to that section, solving problems on your own, recognizing, and read through. It gives you the idea. This one I guess I left the part in that says strategy, but that's the part you got to be thinking of. Say, after deploying a drag parachute, the airplane's acceleration in meters per second squared is related to that equation right there. So it's going to be negative 0.004 v squared, where v velocity is in meters per second. Determine the time required for the plane's velocity to change from 80 meters per second to 10 meters per second. So, given, find. So this is actually still isn't even all that bad of a problem, I don't think. So, find the, I guess, delta t between 80 meters per second and 10 meters per second. And what I always tell students when we're going like, well, how much should I write down for my homework? I think a good way to suggest it is that any engineer could pick the piece of paper up and understand what you did, what the problem was and what you did, right? Yeah. So you don't necessarily have to draw an airplane and write all the thing out there, but give enough information. So the strategy is already written up there, right? Yeah, the acceleration is a function of velocity. So, and we want to find time, so that's our indication, right? So if we wanted to find position, we might have used this guy, but because we want to find time, we're probably going to be interested in doing that. So the way to write this out, because this is right here, is to take this equation, and this step isn't necessarily intuitive until you see it done. See a problem like this, is to flip this thing around and go dt is equal to 1 over acceleration dv. Once you see that, it becomes kind of a little easier, right, to understand what you needed to do. But you had to kind of see that. Just want to point this out along the way. This is the trouble with dynamics. That, like, until you see it, it isn't obvious sometimes, right, of what you had to do. Once somebody tells you to do the thing, they go, oh, I got it. So the skill that you want to build up is that, like, aha, oh, now I get it, without someone telling you how to do it, right? But that right there, that step to that step, or knowing to do this, and a lot of times, just like that maze, you just kind of monkey with it. You got to try a couple things out until you go, oh, I got it. And I tell you what, that skill translates to other courses, where you're going to start being better and better at being an engineer, because you're going to get better and better at going, oh, I got it. I know how to do that. So we plug in the things that we know right here. dt is equal to 1 over, and I guess we could take out some things, but I'm going to leave them in here. Negative 0.00204 v squared dv integral, and okay, so what they did for the integration here is they just took this negative and put it over onto the other side. And so this is going to be just times t, because we're gonna let's just start the clock at 0 and go to t. And we could put the 80 and 10 in there, but let's leave them out for the time being. Is that true? No. Look, we are gonna put the 80 in there, because sometimes it's nice because we put a 0 in here. Let's put an 80 in here. But let's leave this as a variable. How do you know to do that? Well, you kind of have to have been solving some problems and see that it comes out right here. So let's see. I guess we took, when you take the integration, I should have made this another. I'll put another line in here. I'm sorry. Integral dt from 0 to t is equal to, and then you go 1. No, I like to actually do this instead. I like to go v negative 2, right? The integral from 80 to v dv. Then I can do the integration to the thing. That's me. I'm still not trying to learn calculus, right? So 0.004 t is equal to, this just becomes what? Negative 1 over v, and we're going to take it from 80 to v. I'm probably not going to use this video. And then you can have t I'll write out the steps. 0.004 t is equal to negative 1 over v plus 1 over 80. And then you could solve t is equal to 250 times 1 over v minus 1 over 80. And then I think you could just plug in 10, right? That should work. They didn't bother to do this. So, but the answer here then is t is equal to 21.9 seconds. All right, so this example came from a book from Bedford and Fowler, and they asked the question, what distance does the airplane travel as its velocity decreases? So that's a little bit more of a, that's not too terribly bad. What you would do then is you would take this equation and you would use this equation right here, right? If you wanted to find the distance the thing had traveled, you could, what you should do though is you should do the algebra and write this as a velocity as a function of time, right? So how would we do that? Let's see, can I do the algebra for that? So we go 1 over 250, which is probably 0.004, right? Yeah. Times t. And then you probably go plus 1 over 80. But then now we need to have all of this over 1 in order to get it to be a velocity, right? Now if velocity is a function of time, albeit not pretty, and then we could stick him back into this equation right here where we would take dx is equal to v dt and integrate both of those. So we put that into there. And we can put the time, after we get done with this, we can put the time into there. We don't want to do it beforehand because we have to do the integral of the thing. That's where I was trying to say you don't want to stick the numbers in right away because you want to see what happens to them after they integrate the thing. And on the solution to this, by the way, they put a graph on here and they say, okay, well, here's where the velocity is and here's the time, and then we see that it starts to, like right here at 10 and like right here at 80, it kind of starts to dip down, right? So right there, that's where the answer was. Graphing these can often give you a better understanding. We actually skip over the section. There's a section in here about graphing. I'd like to include it, but in terms of how many classes we have in the semester, we just can't fit it into the thing. Anyways, anybody have questions? I'm talking too much. I'm gonna have a problem now where I want you guys to try it. Is that okay?
Mm-hmm.
All right, cool. How are we doing so far? 135, cool. It's too much like the other one. That one's a constant acceleration problem. Let's do this one. This is one we haven't seen. You haven't seen yet. It's in the book though. I also have other problems. Well, let me try the other problems. Actually, let me do that. Okay, so I'm riffing here. One of the, I'm not sure if all the professors are doing this. I suggested to them that they do it for my class. They're there. I want you to, I really think it's a good idea to do additional problems and not just homework. I know that sounds insane. That sounds like a crazy person just said that, right? But let's try it out anyway. I mean, you know, you don't have, because you're not turning them in, you don't have to be neat or anything with the problem. And I give you the answer. The answer is actually in the back of the book of these. But these were problems that or ones similar to ones that we've given as homework before, and we're just not doing this semester. So try out this one, this guy right here, problem 1117. Start writing down your approach to the thing. Oh, I just erased those guys. I wanted. This is gonna be a terrible video. I'll do it while you're doing Just less music. By the way, in a lot of advanced classes, springs and little blocks, use them all the damn time. They would drive you a little nuts in terms of like modeling the real world. Try to model everything as if a spring, a mass, and they add a damper in there too. So you end up seeing lots and lots of problems that way. If you haven't already, I don't know if you noticed, people seem obsessed with these little blocks within the springs, like in vibrations and control systems. Also even weird things. You would think, why the hell do they have these blocks? play baseball, softball, and while you're on deck circle, you hold 2 bats, or you put a little bat weight on there. Same thing here, man. Try a hard problem, frustrate over it, then go back, try the easy problem. Or less hard problem. Anytime you guys are you feel like I'm stuck, I just don't know what the hell to do, and I'm just gonna wait until you tell me how to do it. Just let me know when you're at this stage. I don't want to make you feel angst or punished or whatever. This is supposed to be a helpful session, not that. Of course, the class is supposed to be helpful too, right? So try to.
I'm confused.
Okay.
Because they gave us the acceleration in terms of position,
Mm-hmm.
and then they want us to find position and velocity as it relates to time.
Mm-hmm.
And,
Makes it tough.
yeah.
So it almost because there's a trick somewhere along the way. You have to identify, yeah, there's a trick. Somewhere there's a trick. Gotta be something. It's a good thing to know though, to know that there's a trick. Once you identify, aha, there must be a trick. Then you start to be on the lookout for what could the trick be? What could be the thing that's like the linchpin to like do the thing? And once again, I go back to that maze analogy. Just try something. Just try out what you think might work and see what happens. And see if you land some spot where that all of a sudden you go, oh, I see what I can do now. I wish I had written this one out ahead of time, because I see what I feel is a trick. There's an algebra thing going on here that's I need to sit down on my desk and do. I can't do it live, but I'll start working through it. What do you think? Should I start now, or do you want to keep going? No? I can start. Okay, so we're given that the acceleration is 100 times 0.25 minus x. And we're also told that at the time is equal to 0, v is equal to 0, and x is equal to 0.2 meters. This is in meters per second squared, and this is meters per second, and seconds, and so forth. So, and let's do the find here. Find, and as Annabelle mentioned, we're trying to find x and v at t is equal to 0.2 seconds. So it doesn't seem to be, you know, when looking at the different categories of things, we don't quite, I'm not quite sure I know how to do that, but let's take what we do know, that this is an acceleration that's a function of position, and so it's almost certainly going to involve this equation right here. You agree? Mm-hmm. That's like a clue that we had to work with, because that we know that we could take the acceleration dx is equal to v dv and integrate it. So integral of, you know, we could stick 100 on the outside. Actually, I'm just going to write down what they have on the solution, because I'm going to screw myself up if I try to do it the way that I don't like how they did this, because I don't recognize this integration. There's a better way to do it, I think, but I don't have it written down, and I'm just going to fudge it up if I try to do the algebra live. Is that okay? Mm-hmm. I hate that. I wish I had worked out this problem. Now looking at it, I will write this out at some point. So I'll write it out the way that they have it, where they kept the 100 here, and they kept this together. I multiplied them out and then did them as individuals, but apparently, according to this right here, let's write this in here, v dv, and we can put the limits of integration are going to be from 0.2, no, 0.2 right there. That's why they have the 0.2. Not confused, they're both 0.2, that's weird. Okay, it is true, okay. So that's why we're using 0.2 right here, and then 0 here. All right, and the bottoms of these things match. And let's keep this as a variable, keep that as a variable. They tell me, and this is, like, I don't remember some of these things off of the top, that this can be found to be negative 1/2, 100, and then 0.25 minus x squared. I don't remember that at all. But I bet if I found an integration table, it would be like, I hit one of those, oh, okay, I remember that. Does anybody remember that integration? That you would integrate that and it would become this?
If you just do it, I was trying to solve it by the integration where I was just integrating it, where I ended up with like 1/2 v squared equals 25x minus 50x.
Yes, me too.
Which I think would factor.
I think it would too. That's why I'm saying that I'm copying it off of this instead of doing what you're saying.
It's a weird way to factor it.
Yeah, I don't know why they're doing it. I don't. But that's just, you know, really the reason why we even have this topic. Like, I don't think there's an exam problem that's ever done that we've ever used this, you know, this topic as an exam problem. This is such a great introduction conceptually to why dynamics is hard. It's the maze thing. You don't know how to get to where you want to go initially until you try something out. Write some stuff down on paper, and then it'll suddenly come to you. Because what we do is now we're going to have velocity as a function of position, right? Once we get velocity as a function of position, we can use this and get. I just saw what you did. Did you see that thing? The aha.
It was I was very close, and then I was
very close. But this is the skill set. That's the skill set right there that the whole course is trying to develop. That you work through the thing, not knowing how to do something, and then maneuvering your way to finding it. That's my whole career was that. Boss would give me a job to do, I would be so scared. I'm like, I'm gonna be shown out to be a fraud. I have no idea how to do that. I'd walk to my desk or my cube when I was younger and just sit down and just stare and go like, maybe I should start looking for another job. I don't know how to do that. But then I'd get over it. It's like, you just gotta do it and just try to freaking figure it out. Just figure it out because you had to. And then you know what I got? I got better and better and better at just figuring it out because I had to. That's the definition of an engineer. The scientists think that, well, they don't want it. Oh, we could do that. Oh yeah, then try it. We are problem solvers. We solve problems that haven't been solved yet. Why? How do we do it? How? Boy, you must be a genius to do it. Like, I don't know, I'm not even all that smart. But I know I could figure it out if someone tells me I gotta figure it out because I know how to figure stuff out. I know when I don't know something, then I go ask someone. Right? But anyway, so here you go, right there. There's the big idea. Does everybody understand what the big idea is here? They got 1 over the velocity dx, right? We can arrange that. So what we could do is now we could take velocity after we've done a little bit of manipulation here. We don't have to see the whole thing done out, but we can write that we can know that this is going to be actually plus or minus 0.5 square root. You could just take my word for it. After doing some manipulation, we would be able to get, oh, yes, I got that right. We would be able to get to there, right? Some manipulation we'd be able to get here.
Would it be a 400 or would it be a 1?
I think it's because, well, these guys are going to cancel each other out.
Because, oh, you've got the 0.2.
I think it's a 0.5 right here.
And it's got the 0.2 from the...
Yeah, the 0.2 has brought that into there. I don't know, I'm just writing down, I jumped a couple steps.
Yeah.
But the concept behind it is there, right? Just, you had to get the algebra right into here. But now we can stick this into here, integrate both of those right here. So we're taking the integral of t dt, which is going to be t, easy enough. Here's the ugly one, right? That you would have to take the integral of, oh, I don't even know how I want to write this thing. I guess, yeah, they went ahead and wrote it this way right here. Oh, well, actually, okay, let me write the thing out, which in their method. Yeah, okay, dx over 0.5 square root. And they kept the plus or minus in there, which I find is interesting because probably what you do that for is just in case the positive one ended up giving you a negative result, right? Because, well, that obviously wasn't true. So you keep the negative one in there because you know that the time is well, no, okay, because they have the time is 0.5. Yeah, no, you still, yeah, at some point you're going to have to take, anyway. There can be 2 answers for things, right? Because you could possibly have like something like this right here where you could have like, or I'm sorry, something like this right here because this time, right? So it could have like this right here. So you could have a possibility of having two separate results. Like it could either happen this or it could happen that onto the thing. So just, that's probably why the plus and the minus has been kept in there. But we worked through the thing, and they note that this is a, boy, I hate this, that the form, right, the integral form that they use is going to be, looks similar to t is equal to the integral of du over square root 1 minus u squared, where we've established that u is just to replace with the thing, right? So like that would be the integral form that we would use. And the results are going to be ugly, but doable. It's ugly, but doable. This integral form right here ends up being actually a sine wave. 1 over 10 sine, and actually an inverse sine. That's interesting. Oh, but that makes sense. Sure. Okay, from I left the 10 out that they put into it right there. But there is, this is right here. The form of the result. The actual result looks like. Why did they use u? Okay. The actual result when they get done with it, and they work the thing out, and they solve the algebra for the position, is going to be x is equal to 0.25. And by the way, I will write this out on my own longhand, all of this right here, so you can see the thing. But I just want to talk about the concepts, not necessarily all the individual steps that are working here. I also want to take a step back and, all right, so there is the actual thing that would be working through here. After we integrated this right here, and then we solved for the position, we would have this as a form with respect to time. Then we could take the derivative of this. So you go dx dt. And what you would find, you'd have 1/2 sine of 10t. Right? And then you would plug in the value of t is equal to 0.2 seconds, and you'd get the position is equal to 0.271 meters, and the velocity is 0.455 meters, right, per second. Something that's interesting about the problem, interesting being, how interesting could it possibly be, is that this is actually what you find almost always with this problem. Have you taken differential equations yet? Like last year?
In the fall.
Yeah, in the fall. Yeah. I took it undergrad, and then I took it for my master's degree. And then, and I felt like I was taking the same class over and over and over again. And well, I made pretty good grades, and I don't remember what my grades were, but I made pretty good grades different, but I never really understood it. And then for my PhD, I had to take a math class, an advanced engineering math thing. And the instructor said, do you know what this differential equations, what we're really doing here? And I'm like, It was a big class. A lot of people, they all seem smarter than me. Always felt that way. Right? Like the dumbest person in the room. Turns out lots of people feel that way. He says, differential equations answers the question, what kind of thing does this? And I'm like, oh, I get it. Okay. Like what? And one of the rules in differential equations is I'm trying to think of the name of it. But there's a test to make sure uniqueness. Like it's a unique solution.
Linear independence.
Yeah. Well, not necessarily in linear independence, but just unique. Like there could not be any other thing that would do this. But linear. Yeah. So when you say the most simple of differential equations is F equals ma. Right here. And that's what this is right here. We're not doing that in this class. In vibrations class, we do this. And you actually should be taking vibrations class at the same time as differential equations, because then you think, that's the reason why differential equations exists. Like what kind of thing, and so like, you know, you rearrange this like this way right here, you go K over M right there. And then you take different, you try to find the solution to that. You go, what, and the solution is, what kind of thing does that? What kind of thing, when you take the second derivative of it and you subtract out the original thing, will equal 0? What kind of thing does that? And the only answer is a cosine. A cosine, when you take the second derivative of it, turns into a negative cosine. Right? So if you were, or a sine, right? Don't worry about the sines onto the thing, right? But anyway, that's the only way that it works out. That's the only thing that can do this. Hey, lo and behold, it's a cosine, right? The system is a cosine. So they actually formulated this problem correctly. They probably went backwards to do it, right? To get and figure out how they could make the acceleration a function of position. But it is a function of position because the force on this is a function of position because this is a spring. When the spring changes its position, the force changes, right? And force is equal to mass times acceleration. We're going to do that in the next section when we do particle kinetics. Anyway, so, but that's stuff coming up, and not necessarily, and this is even in vibrations class. We don't even do that in this class, although a lot of times when you teach dynamics, there's a vibrations section. There's a chapter in vibrations in here, but because we have a class for it, we don't teach it here. But do you get the big idea with the approach? What's more important than anything else is that we get that approach and the big picture approach when it comes to the course. Well, we're done. I'm sorry, we went over. I apologize for that. I thought of it as being 1 hour long. It was actually 50 minutes long, so I went on way over. But I hope you'll consider coming back. I hope this is useful, and I hope this helps with your homework, and that you'll consider registering for the course. By the way, you can register your course and not come. It's not necessarily that much, but it'll feel like a little bit more of a commitment. You get like little announcements through the thing.